data points to include and not include, see? So it marks different points good and bad as it moves around. Of course, this model doesn't ever explicitly mark data points as good and bad, but it effectively does. Your choice of M and B puts data points into the good and bad bins. And that's why you get multimodality. That's very common in these problems. I have many more things I could say about that, but I'm not. Oh, one thing I should say here is plain old MCMC. That's one hell of a bad posterior distribution function, but MCMC had no trouble with that. It didn't mind that there were multiple minima. And the MCMC found the multiple minima and populated them and gave me a posterior distribution function that's pretty ugly.
How many steps did you actually have to take?
I think this is on the order of 1 million, maybe 10 million. It's a large one. And I didn't check carefully that this is converged. And my idea of converged is, I make my, this came up earlier. How do you know you're converged? Well, as Phil said, there's no very clear way to do that. But one thing you can do is you take your 1 million samples, you get this. Now you take the next 1 million and say, does the plot still look like this? And I only did minimal checking of that, so I'm not actually sure that I'm converged here. It might not be converged. But it is clear that it's finding multiple maxima and it can deal with those multiple maxima. Okay, so how much time do I have left? A few minutes? So let me say one last thing. Okay, so now, the problem that you really face. So you all have had the situation of fitting a straight line in the case of outliers. People know about sigma clipping. Sigma clipping, I officially do not endorse. It's officially a very bad idea. It does get the job done. It's noted to get the job done. I've written many papers based on it. Yes?
Before you continue, may I ask a question? Because instead of taking the sum of weight of least squares and then do sigma clipping, people often do what's called the median.
Yes.
Because the median is not sensitive to a single outlier or something.
Exactly. So again, the median, so good. So the median, there are various methods that are like quasi-medians. Of course, in 2D, there isn't any clear definition of the median, but you can take pairs of points and find all the slopes and take the median of those pairs, or there's various things you can do with medians that might work. And of course, I object to that because it's a procedure and not the optimization of an objective function. So on basic grounds, I object to that. But of course, I also object to it on practical grounds, which is that you don't actually know that your outlier distribution respects the median. It may be pulling the median. Now, it is true that in general, median statistics are very robust. So I'm not going to argue that you're likely to go way wrong using medians. Medians are very strong. But if you want to understand your data, you have to model them. Still my opinion. Okay. Yes. So, the second most common situation, well, actually I was saying that all of these assumptions are broken in practice in every real astronomical problem, but let me talk about another one. So let's talk about errors in both directions. Okay, so now the idea is, instead of having a data point here that has an error bar only in one direction, what you have is a data point here with an error in this direction and an error in this direction, and they're probably covariant. Right? So you have some ellipse. So let's assume we're still Gaussian errors. We still know the errors. The data still come from a straight line. Everything's the same, except that there's errors in both directions, and those errors are covariant, and they're different for every data point. So this data point looks like this, then there's another data point that looks like this, there's another data point that looks like this, and another data point that looks like this. And now what we want to do is find the straight line that goes through these data. That's the best fit to these data. Right? Now, what's the model now? So it used to be that we could just say, this data point has this x value, because the x value is perfectly measured, and it's just a question about where the y value is offset from that x value. That used to be our situation. That's no longer our situation now, right? Consider this data point. Actually, let me draw a more isolated data point. Consider this data point. This data point is thought to be something that truly comes from this straight line, but it's been offset from its true position by a two-dimensional Gaussian arrow. Right? So that means this data point could come from here, could come from here, it could come from here, it could come from here. Right? Any of these are possibilities. Right? We don't know. What do we have to do? We have to introduce a model parameter for every single data point. Right? Which is, where is it on this line? You see why we have to do that? Because we can't assume that we know anything about this data point could have come from anywhere and have been offset to here by its Gaussian arrow. So that means there's an additional one full free parameter per data point, which is where it really is, the really truth of that data point. Okay? Now, in principle, that means I go from having 5 parameters, because I'm still going to do my outlier rejection, of course. So I have 5 parameters, I went from 5 parameters to 25 parameters. Does anybody have any suggestions that might help me here? Yes?
I don't have a suggestion. I have a problem with that because with a sufficiently sophisticated model, I can then detect anything.
But that's true. Absolutely. Indeed, I could say that these data points come from an arbitrary curve in 2D. But I'm not assuming that. I'm assuming that they come from a straight line. So I'm assuming a very restrictive assumption here. And I'm assuming, in fact, moreover, that we have a reason to believe assumption 4, that the data really do come from a straight line. So I am not giving these data points the freedom to come from anywhere. They still have to come from this straight line. The only question is, where along the line do they come from? See what I'm saying? I'm only asking about one dimension of their position. And these are two-dimensional observations. So I'm going to argue in my third lecture, by the way, that you don't need to have more data points than you have parameters. You might think that you do. But in this case, we have more data than we have parameters. Because though I added a parameter for every data point, the data points are now two-dimensional. And I only added one parameter per data point. So I have 25 parameters now, but I have 40 measurements, all the x's and all the y's. So I'm okay in that respect. So it's still a very restrictive model.
I don't understand. What's the extra parameter you're adding for every point?
Where it is along this line. This object came from somewhere along the line, which is perfectly obscured by the video camera for you. Do you want me to move this
No,
now?
I'm good. I'm good. I get it.
So, right, so there's a parameter. I don't know where this data point. In this case, when I was doing one-dimensional, x was perfectly measured. So I knew that for this line, this data point had to be coming from right here.
Okay, so you got some single parameter going along the line. And just, okay.
Right, there's some parameter along the line, right? Yes?
But in that formalism, then there is still room for outliers, because in principle, then every point comes from the line.
Well, that's true. It's true in this case, too, right? Every point came from the line, but then we added the outliers, because clearly some of them didn't come from the line.
So you still have to quantify the probability that it really was shifted just by
Exactly. So again, we're going to do a mixture model. We're going to do a probability that it is in the line, plus a probability that it's not on the line. We're going to do the same thing. But I've already added 20 additional parameters, which are this here. But can anybody give me a simplification? Somebody who is in Heidelberg, who saw me speak about this before. Let's see if anybody remembers. What's the simplification that makes this easy?
So you are measuring with the same instrument, so you can correlate the measurements.
That would be nice, but I'm actually going to assume, here, let me show you the data I'm going to fit. Here are the data I'm going to fit. I'm assuming that every data point has its own unique error bar with its own unique covariance. Okay, so here's the deal. There's an additional parameter for every single object. So in principle, I could do a 25-dimensional MCMC and then plot the results. Warning, that would take a long time. That would not be impossible. People do much more ridiculous MCMCs than that. But there's a geometric fact here that's very simple, which is that if I integrate over this parameter, imagine I'm integrating over this parameter, what's the same as doing? That's the same as integrating